Okay, so today I'm going to talk about several tricks on big data debugging tutorial. So this is something that you will encounter in homework because you are going to work with relatively large data set. Um, and the key here is these are the tricks can help you understand why your code is so slow and how to speed up your code. Um, I mean, this is very important. And later on you will see. So this is and becoming more and more important. Um, I mean, if you didn't program it well, it might take significant longer hours or more than it should be. I mean, if you program correctly, that only take about seconds, right? So this is quite a dramatic differences. So first, we are going to import all these libraries. We're going to import the NumPy. We are going to import the matplot library, and we also import the times to like track how long does it take to run this and a specific piece of code. Here, right here, we're going to load the MNIST data set. So we're going to be using this data set a lot in the future of the homework and the lectures as well. So here is the way that we're going to load the training data set and testing data set. As you can see, we will have 60,000 like training data set and 10,000 testing data set. So these data set are 28 by 28. So this is so each and the data is an image. So and what you can do is you can actually plot first line of the image in the order of the and a 3 by 3 grid. So you can see the first and the first one is actually the image of 5. The second is image of 9 and so on. So these are all handwritten digits and images. So I believe you have seen this before. All right, so here we're going to using a very important concept called like distance and a matrix. So this is basically to calculate the pairwise distances between a set of vectors. So basically this Dij is distance between Vi and Vj. So you can think about Vi and Vj is some and the vectors ith and j. So this distance is basically the norm we have a talk about in the previous and reviews. However, as you can see, the most commonly used and the distance is Euclidean distance. But later on, and you will see sometimes in some situations, maybe Euclidean distance is not the best choices. So it might be, it might be the it might be not the best choices sometimes. Okay, so all right, so so let's try a very simple like methods, which is k nearest neighbors. For example, if you are coming with a new image, so what would you do is, the simplest way is we are going to calculate the distances between with the new data versus all the training data, right? And find out the corresponding maybe k nearest neighbors in the training set, and we are going to ensemble and the labels of this k nearest neighbors to make predictions for this new data. So the whole idea is very simple. We can predict the class of any given data by looking the class of nearest neighbors labeled and the data point, and of course, and that will be and we're going to pick k of them, and whatever the class is most common and within this k nearest neighbors, that's the class we're going to predict for this new data point. But the key is you can see we actually need to find out these k nearest points that we're going to using the distance, right? So and obviously the distance is very important. So in actual applications, in fact, and later on we're going to talk about this k-nearest neighbors in detail. There will be n like labeled data. So this is your training data, and m unlabeled data. So these will be like some like testing data set. And in general, we can think about this data is in dimension of D. D could be very large. So in this cases, for this like image, and each data is 28 by 28, but but we have to flatten this image into a giant vector because we cannot compare with the distance of two so matrices. So we're going to reshape this an image into 28 times 28 by 1. So this will be like, and as I believe 784 and the dimension. So this is quite big. So this like D is like 784 here. All right, so basically in order to implement this k-nearest neighbor, we actually need to calculate these distance between these labeled and unlabeled pairs. So basically all these distance will be stored in this n by n matrices. So basically this Dij is the distance between ith unlabeled point and the jth labeled point. So these are basically says this I is corresponding to the index of unlabeled point. J is corresponding to the like labeled point. All right. So this is basically how we find it out. And since we have an X and Y, they are all like, so that's my data matrix. So this is just being like nxik, yjk, and square them and sum all and each component of the D from 1 to a D, then take the square root. That will be my Dij. So you think about for each ij, I have to solve this and a rooming square basically. All right, so what we do is, and obviously we are working with very large data set, 60,000. We don't want to work on the 60,000 data set. So immediately, because if you don't like a program that efficiently, you might have a trouble. So this also happens to later of the courses here. If you believe your code is not efficient, maybe you should just take maybe 2,000 data sets or maybe 100 testing data sets just to test and have a quick test about this running time. Sometimes you will find out that there will be more an efficient way to implement your algorithms. But if you want to always debug with 60,000 data set, it will take forever because maybe each run will take 20 to 30 minutes. That won't be efficient at all. So if you only have 2,000 data set, it will have a very quick turnaround. So it can tell you whether your code is efficient or not, like very quickly. Then you can scale up to 60,000 data sets if you need it. And then what we're going to do is we're going to take a subset of 2,000 of training and I believe a 2,000, like 200s of the testing data set. So N1 is 2,000, N2 is 200. So what we're going to do is we're going to take three possible and a strategy here. So the first strategy is I'm going to subsample of first an example. Basically, I'm going to just take the first n element of all the data. So and say we choose n equal to 2,000. I'm just taking the first 2,000 data sets. All what we can do is we can randomly subsample this data. So basically just sample 2,000 data set. And with that, all what we can do is we can do this like stratified and subsamples of data and using the scikit-learns, right? So this is and the differences here. So so like the difference is if we try to do the stratified and a subsampling, and versus this like random sampling is for this random sampling, these indices could be repeated, right? It's possible that we have like repeat those like in the data in this indices could be, for example, and the number 2 may shows up twice. And of course, if my n is really large, usually that won't be the problem. Sorry, if the like and the length of x is really large, usually it won't be a problem. But if the data is relatively small, you might see those data being repeated. And again, but we know this is not biased at all. So, but stratified and a subset is always like we own. And once the data is being picked out, then we're not going to pick this again. So these are like 3 different like samplings, like strategies. So what we can do is we can just see like and a class distribution as well. So and since we are going to sample, like I believe in this case is 2000 data set, we're trying to see like what is the distributions of this 2000 data set, and precisely. So this will like just simply return the class distributions. And you can see if we do this way, and there's not much differences here. And everything is all around this like it's like 10%. It's almost 10%. And whether you choose the first n subsample or the random subsamples or stratified subsamples. So you can choose any form that you needed. But in order to like speedify the debug, it is recommended to using stratified of subsamples of the original and the datas. But if you, but you can use any like data samplings if you need it. Okay, so what we do is right here is, and of course we don't actually need to and the labels to compute these pairwise distances. So so what we can do is we can just create this like stratified subset for on the it's x train 1, y train 1s. And the way that we do, and the first things that we need to do is we need to flatten that. So this has something, and we have a talk about this. So basically, and here we have and a 2000 data set that will be 28 by 28. And we need to turning this into 2000 by 28 times 28, which is 784. So this is, and we need to flatten each image into vector such that we can calculate the distance between and the 2 images. So this is very important. This is the very important part that we have that we will do that in the futures. And all these images, data, we don't, except for later one, maybe in 593, we talk about convolutional neural networks, and we don't like reshape into a vector. But for 592, the machine learning courses, all the data of images are being reshaped into a vectors. And then we can just apply all sorts of machine learning algorithms directly. All right, so that will be the data that and just like pre-processing of the data. The first trick is we just blindfolded, just like and explicitly implement this formula right here, which is Dij is equal to square root of this summation from 1 to the d. D is 784 here. And this will be xik minus y and yjk squared. So basically, this is like one loop from 1 to the d, and this only contribute for 1 entries of Dij, but we know I is from 1 to the m, j is 1 to the n, so this will have a triple, like 3 loops, and that to fill up each entries of the d's. So right here, so this is actually the implementation for three loops. We have a loop of I, we have a loop of j, we have a loop of k. This is the simplest. It's like you don't actually think anything. Just like and literally implement that. But the issue is if you just for this 2000 by 200, I believe, this will take about 235 seconds, which is almost like I would say 4 or 5 minutes to run. This is really expensive, we only have a 2000 data point and the 200s for the testing data. We only want to calculate the pairwise distances here. It will work, but it's not efficient. And the point why it is so expensive, is because NumPy itself is not optimized to do these kind of for loop. Every time you see a lot of for loop, it will significantly slow down your implementations. So I would suggest if you like trying to implement everything, the first thing that you should try is, can I vectorize it? If we can vectorize it, it will be very likely to and speed up your program, because NumPy is being it's very optimized for those vector calculations and the matrix calculations. So what we can do is we can replace this inner loop for the k into to vectorize it and just being like and subtract of these two vectors, then square them and sum them together. So this is basically we replace this inner for loop and it becomes a vector and operations. So we can do like and basically the same thing. So we can save one for loop now and everything is being done into two loops. And you can see this actually significantly speed up. So if we mute this thing and just change these like two lines, it actually reduce the running time from nearly 4 or 5 minutes into 4 or 5 seconds. Like this is very significant. It's crazy. But also like for this part, we also talk about how you can debug your data code. Usually, this is not like local ID. You can using PyCharm, Visual Studio to do debug if you need it. But if you actually using Colab, there's no way that you can debug easily. So the simplest thing that you can do is you can using some PDB, which it can actually debug it for you. It can just and help you and to understand where. And this is basically if you do PDP set a trace. This is basically set a breakpoint. So once you set breakpoint, that means your code will just stop at this point that you can run like in a step by step. Okay, so and this like PDP is the way that actually can helps you to like set a breakpoint and help you to debug. All right, so you can see this is significantly improved. In fact, we can do even better. We can get even like get rid of everything for the j through in the loop here. So that means if I take the ith entry right here, and what I'm going to do is I'm going to using like broadcasting rules in NumPy. So basically, this xtrain1 is actually a matrix. This xtest1i is a vector. So basically, a vector and subtract a matrix. So that means it will subtract each row of the matrix automatically. So if we leverage this broadcasting rules, and we can get rid of this for loop because for the loop of j, it's basically equivalent way of the broadcastings. So basically, it automatically did that for you. You don't need to do it like line by line. as a result, you are getting this and and you can get rid of one loop. I mean, if you do this, so this is basically, as I said, is using broadcasting rules. You can check out what actually is broadcasting rules, and give you some idea. And I mean, this is very important because you're going to see these things again and again. I mean, of course, if you don't understand that very well, you can always ask ChatGPT to give a good explanations what is that broadcasting means. And sometimes I will get confused. I will ask and like Google's what is the broadcast and what is the right way to broadcast my variables. Okay, if we run this, and this will only take about 2 seconds, which is and reduce from 4.6 to 2.1, right? It's quite significant improvement as well. On the other hand, in fact, we can do even better. So basically, we don't even need to do any loops. So so the magic is we just like look everything carefully. We basically see this is, and we can split these things up, and this can be written as xi's inner product, and subtract 2 xi's yj's inner product, and plus yj inner product. Okay, so for on and all combinations of ij, this middle term right here is quite unique, but this like and xi and yj terms, it's being repeated again. So and so that means if we can just pre-compute these things, so we can just store that, right? So we don't need to recompute these things again. So basically, and what we can do is we can and even compute everything else like an xi and so like norm of xi and inner product of xi and yj and the norm of yj. So if we can pre-compute everything and save them as a separate number, so as a separate matrix, and we can just add them together, I mean the right way, so when it is needed. And all these things can be done without using any loops. So so this is the way that you can do. I don't want to get this into too much detail, and it also is actually and you need to use this kind of broadcasting ideas. So basically, if we have this like x2 and the y2, they are all becomes the calculate and the calculate norms of x and y's, and this and xy is basically the inner product of xi and yj, and save this into the matrix form. So this is quite simple here. And the most important thing is this whole thing is just being calculated once, like just once, that will be enough. And all we need to do is, and later on we're going to take advantage of this and broadcasting techniques, and this becomes our trick of x2 minus 2 xy's plus y2. So this is basically just simple and linear and calculations of these and vectors and the matrices. But of course, this is quite tricky. And this is, I would say, not that straightforward. You actually need to use some broadcasting ideas. So that means this x2 right here is actually need to reshape from m as a vector to the m by 1 matrices. And then we can do all these things automatically. I mean, this is very clever, but it's quite tricky because you need to understand this broadcasting rules extremely well. I mean, if you do this no loop things, it only take about 0.3 seconds. So this is very, very significant. This 0.3 seconds versus 2 seconds, right? So this is about like at a 40, 50 and times faster, okay, than one loop. But of course, this is way too advanced. So in the homework or in the future of the things, I will expect you can do one loop. So And I know most of the cases, one loop will be, good enough. It can done and a very good job with one loop. For this two loop, it's okay, but it's not really efficient. But in any cases, you should avoid three loops situation because this is way too expensive. It would take forever. All right. So and think about for like 2,000, or in that take about 5 minutes. And how long and does it take for the 60,000 and the data? That would take really take forever. And you might have no chance to finish that. All right, so and then we can actually do this comparisons to see this D0 and D1 is actually all close. So basically, and that means we are actually getting it right. Okay, so let's do K so K nearest neighbors and a classification here. So what we are going to do is so we know this is m by n, right? So this is m by n. So we should have m rows. M is corresponding to training, n is the testing data set. So that means for each testing data set, and we're going to sort for each of the and we're going to sort for each columns right here, right? So that means the way to sort for each column is you're going to do the argue sort of x is equal to 1. That to indicate I'm going to sort in that matrix column wise. So these will be the neighbors of that. Then what we're going to do is you're going to choose the 10 closest, so k equal to 10. And we can see these are the 10 random and the closest neighbors for that. And for example, and for that with the force, these are the I believe that's the and that's the top and the top 10 images being closest to this testing data set. We can see, and so most of them are 4. And this is the top 10 images close to 1, which is right here is most equal to 1. So you can see if we're using k nearest neighbor, it can predict this pretty well, right? With the k equal to 10. And you can see in terms of and the majority, if we choose the majority rules, it can and do this and the result pretty and efficiently. So this way we can write down our prediction functions. So basically for each testing data set, we will select the closest the k points, which in this case will be k equal to 10, which is first the k columns in the and the closest neighbors will have and the k nearest neighbors. So we're going to choose the label of the close neighbors of the training data set and use this majority vote to see which digit and appear the most for that. So this will be straightforward. So what we're going to do is you're going to choose this sorted neighbors for the top and the top k and the top k of that, right? So this will be and this will be the situations that you're going to work with. Okay, so then you're going to and get this and the corresponding labels for the training data set. And then what you're going to do is you're going to this and a bin count and apply into the axis of the one which is the column. If you do this, you are getting and calculate this accuracy, and we can do any predictions for k and k equal to 1, 2, 3, 4, 5, 10, 20, 50, and 100. So you can see if we actually plot this out, you can see the accuracy will start to increase, then gradually decreases, and for this testing data set. So that means in terms of the optimal k that we should equal and that we should choose k equal to 2, because if we choose k equal to 2, that means my test accuracy is reached the maximum right here. So this just, and we're using, and this trick is called and cross validations to tells us what is the best and the k, I mean the k nearest neighbors in the situations right here. Okay, so this is basically a very quick overview how we write down these predictions for this k nearest neighbor, obviously without using any kind of scikit-learn packages here. All right, so let me see. Wait. Oh, I think I make one mistake here. M here is the number of testing points, so this will be 200. N is the number of training, and the point that would be 2000 right here. So D will be the features, which is the 784 here. So this D0 right here is it's the matrix of the size of 200 by 2000. Right, so that means for each row, that will be calculate the distance for this particular testing data set with each of the training data set. So I mean, if we extract the first row, that will be the first testing data set, and calculate the first testing data set. I mean, distance of first testing data set with other training data sets. So that means I was wrong. Sorry about that. So if this D0 argue sort is basically sort along the rows. So I mean, it's sorting in the increasing order of the distance. So that means if we pick and sort this way, so it will sort row-wise for this D0 for each rows. So this will be sorted neighbors. So that's why in this predictions here, so that means for each row, we are going to truncate up to each kth column, because on the first kth column, that will be the k nearest neighbors. So that's why this top k neighbors right here, you should be getting 200 by k, right? Depends on the choice of k you here. So that's why your top k labels is also 200 by k's. Then you're going to do is you're going to using this majority rules by doing bin count and find out what is the maximum values for this bin count. Okay, and this is basically the majority rules that you are going to apply here. Okay, so that's why this is how you actually write down these predictions for the k nearest neighbors. And then later on, we're going to implement this and from scratch in a detailed ways. But I want to emphasize this is some trick. It's quite advanced, and you can see right here. And usually you actually need to have a good observations of your problems and the models and the mathematics. So with a good understanding of everything, that you can help you to actually implement a much more efficient algorithms. So that's why, in a lot of cases, when you do homeworks or projects, whatever things that you're working with, not only it would should be accurate, it also should be efficient. Okay, and otherwise, once you hit the much larger data set, your program will take forever to run. That will be also a big problems. All right, so that's all for today. That will be the end of the lecture 2 here. All right.